Let's look at how the binomial expansion can be extended to A2 maths. So as you can see here, we want to find the first four terms of this expansion. However, we don't have an integer power like we had in AS. So what we're going to do is we're just going to treat it using exactly the same strategy as we did before. However, we're going to start off by just simplifying this a little bit. Last year we always had, say, 4 to the power of n, and then 4 to the power of n minus 1, and calculating all that can just take a bit of time and be a little bit tedious, especially if you've got non-integer coefficients. So we're just going to start off simplifying this and pull out that factor of 4. Remembering, however, that is 4 to the power of minus half. Everything in this bracket was to the power of minus a half. Because we've pulled out a factor of 4, this is now going to be 1 minus 3x over 4. You can now see when we do our expansion, we're going to have 1 to the n lots of times, which we know is just 1. Much, much easier. Okay, so let's look at how to expand this. 4 to the minus half is just a half. That's going to be outside of our brackets, and then we can do the expansion. First term will just be 1. Nice and simple. And now we'll proceed doing what we did last year. So we have the power. Don't worry that it's non-integer. The method works exactly the same. Multiplied by one of our x terms. Notice that because we've simplified that to a 1, we don't need to worry about 1 to the n anymore. It's all fixed for us. That's our second term. We can now get the third term. So just like last year, we have the power times the power minus 1 times by our x term squared over 2 factorial. If you can't remember where this process comes from, check back to last year. We'll discuss in lessons why this can be extended to non-integer coefficients. If you're doing further maths and you do Maclaurin expansions, you'll see in much more detail why we're allowed to do this. Okay, and then carrying on the pattern, minus a half, minus 3 halves, minus 5 halves, minus 3x over 4 cubed, all over 3 factorial. Maybe you want to put in the 2 factorial there just to remind yourself that it is a factorial. We only want the first 4 terms, 1, 2, 3, 4, so we therefore only need to go up to x cubed. We can now simplify each of these terms and expand this bracket. A half times 1 is a half. And then check your sign first. It will be positive, negative times a negative, and then we'll just treat the numerator and denominator separately. So the numerator is just 3x, and the denominator 2 times 2 times 4, 16. Again, check your sign first. Negative, negative, negative squared, positive, x squared. Numerator first. 3 squared is 9, times 3 is 27. And now the denominator, 2 times 2 times 4 squared, 16, 32, 64, 128, 256. Sign again, negative, 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 negative cubed. It gives us a positive again. And then we'll check our numerator. We can see here that we've got 27. That factor of 3 and that 3 there can cancel out, so we don't need to bother with that. 27 times 5, I'm probably going to get this wrong, but I think that is 135 x cubed. And then the denominator, 64, 128, 256, 512. We've cancelled one of the 3's there to make our lives a bit easier. We've still got one factor of 2 there because it's 3 factorial. So that was 1024, and the half at the front, 2048. There you go. Just extending the method that we used last year with one step of simplification at the very start, so we didn't have to keep having 4 to lots of awkward powers in this. we can expand stuff with a non-integer coefficient using exactly the same method as we did last year. Maclaurin expansions for further mathematicians explain in detail why this works. If you're doing just regular A-level maths, look back at what we did last year, and it's that same idea of pattern recognition, just extended to non-integers. One final thing to mention, we have been ignoring all of the greater powers of minus 3x to the 4. So we ignored that to the 4, 5, 6, 10,058, whatever. It's only valid to ignore those terms if we know they're getting smaller. This will be getting smaller, so I should put that in these, which mean always take the positive, so we call that the modulus, always take the positive. This will be getting smaller if it's less than 1. Okay, so just straight lines mean modulus, take the positive of whatever's inside of it. So that must mean that x, the modulus of x, is less than 4/3. Alternatively, because that's saying always take the positive, we could say minus 4/3. X is greater than minus 4/3 and less than 4/3. So what we'd say is this expansion is only valid for modulus x less than 4/3 because I'm ignoring all of those higher powers of minus 3/4 x. I can only do that if they're vanishing down to 0. They will only vanish down to 0 if it's less than 1. Okay, so when that there is less than 1, higher powers will eventually disappear, therefore I only need to consider the first few. We see that that's only valid for x is less than 4/3. That's how we do binomial expansion at A2.